This is a dramatic reading of Justifying the Love for This Strong Equivalence Principle, a blog by the Stand-Up Physicist available at science2.0.com. The strong equivalence principle is a stately beauty queen of an idea. In the simplest of dresses, she refuses to dance with any other theory except general relativity. The mundane reason for mass is beyond her concern. My own efforts at unifying the symmetries found in the Standard Model with gravity is called GEM for gravity and EM, not to be confused with gravitomagnetism, which sometimes goes by the same acronym. The duality between metric and four-potential theory extends a hand between the metric explanation for gravity and Newton's scalar approach that actually moves up into a four-mansion. An obligatory cancellation inside the GEM Lagrangian provides a field theory justification for the strong equivalence principle. Now, if the Higgs boson is found, this entire house of cards collapses. If the Higgs is ruled out over a reasonable range of masses to 95% confidence, well then go ahead and join this evolutionary step in physics. So let's begin with Einstein's own statement about the weak equivalence principle. A little reflection will show that the law of equality in the inertial and gravitational mass is equivalent to the assertion that the acceleration imparted on a body by a gravitational field is independent of the nature of the body. For Newton's equation of motion in a gravity field, written out in full, is inertial mass times acceleration equals intensity of the gravitational field times the gravitational mass. That is only when there is numerical equality between the inertial and the gravitational mass that the acceleration is independent of the nature of the body. End of quote. Now, as an accounting jerk, I don't give anyone any slack, even the most revered one. No, Newton's gravitational force law, written out in full, I mean that's what he said, includes the rocket science term as an effect of gravity. Now, perhaps even Newton never wrote it out that way, which would really be kind of cool. See, I'm just not interested in a great approximation of the truth. The systematic dismissal of the rocket science effect of gravity reminds me of the collapse of the housing market. Wall Street was given the keys to the money behind mortgages. And the quants there, many trained in physics, they constructed all these great models about how money changed within those markets. And they even figured out how changes within changes figured that out. It moved, And they understood it so well that they sold insurance whose market value was claimed to be more than the money in the combination of the stock and mutual funds together. I remember seeing that and going, that sounds a little insane, but that's what they claimed. And they just forgot to model what would happen if the value of real estate actually dropped, because of course that never happens until it does. So here is Newton's gravitational force law written out in full. Okay, so we got all those terms in there. Great. So so we've got what do we got? We've got an R hat and a V hat. Why do we need the V hat? Well, because we've got a rocket science term, that's the v dm dt, and that definitely points in the v-hat direction. So you got to have that sort of thing. And then I also show my own thing where I do a dm-dr, throwing in a factor of c, and I think that might really be involved in things like particularly dark matter. We'll see. I mean, gravity basically is broken in a variety of ways, and I really recommend this PhD comics version. If you haven't seen it already, it's not on YouTube, but I'll try and put a link in. I hope they don't diss it out. Research basically is concentrated on stuffing the ballot box, adding to the causes of gravity. I want to recount all the votes in the state, which actually worked in Minnesota, but was blocked by the good brother in Florida. So the first tests of the weak equivalence principle were actually done by Galileo, rolling a ball down an inclined plane. An experiment I've actually done myself. It's kind of neat. I should put a caveat here. I didn't really check whether he used spheres made out of different materials, and like glass and wood or something like that. Certainly the kind of thing he would have thought to do. So if he did actually do that, and I wish I had the time to look into it, that would actually constitute a really good first test of the equivalence principle. And if you know of the detail, please contact me, let me know. So everything obeys the same gravitational law, and that's the take-home message. Now, proving that point actually does require the scientific method, because people believe that heavier things will fall slightly faster than things that are lighter. And that gut feeling people have, and we can actually measure how many folks actually accept that to be true, is actually based on merging aerodynamic resistance with the way gravity works to make a theory of falling. Now, when theory of falling, that there is a correlation between lighter things having more air resistance and therefore hitting the ground, falling to the ground later than something that's a brick. Because a brick, the aerodynamic resistance is smaller, all right? So the weak equivalence principle actually is pretty easy to get along with. You just really need a theory that has a metric solution and that only uses a mass m, within the theory. Don't junk it up with things like separate terms for bosons and fermions or chirality or something odd. Make it simple, and your metric theory will work fine with it. But there is something called the strong principle, and that's actually much tougher to come to terms with. The strong equivalence principle suggests that gravity, this is a quote from Wikipedia. The strong equivalence principle suggests that gravity is entirely geometric by nature. That is, the metric alone determines the effect of gravity and does not have any extra fields associated with it. If an observer measures a patch of space to be flat, then the strong equivalence principle suggests that it's absolutely equivalent to any other patch of flat space-time elsewhere in the universe. Einstein's theory of general relativity, including the cosmological constant, is thought to be the only theory of gravity that satisfies the strong equivalence principle. A number of alternative theories, such as the scalar tensor Brand's-Dickey theory, satisfies only the Einstein or weak equivalence principle. End quote. Now, general relativity has that minimalist pole position. No other rank 2 field theory can be simpler. Well, the GEM theory, or work, is trying to get into that exclusive club by working one floor below as a rank 1 field theory. I have shown how the exponential metric is a solution to the hypercomplex field equations in an earlier blog you can find here on YouTube. Rosen developed a theory that also has the same metric solution. Rosen's work introduces a flat background metric. That extra metric breaks the strong equivalence principle. It also provides a place to store energy and momentum, leading to a prediction of dipole gravity waves emissions. And that prediction has not been confirmed in the analysis of gravity wave energy loss by binary pulsars, thus invalidating Rosen's efforts. The problem with dipole gravity waves is a common killer for alternatives to general relativity. Now, there is only one metric in the hypercomplex gravity work. Using the magic math of duality, I have shown that a four-potential solution to the gravitational Gauss's field equation is identical to that using the exponential metric. The duality forms a bridge between Newton that gets light bending around the sun half right. Partial duality is like being partially pregnant. Newton's theory must be expanded from a scalar theory to a four-potential to be dual to the metric approach for light bending around the sun experiments. By working on a different rank than general relativity, GEM has the chance to play nicely with the strong equivalence principle. There are two particles that actually play a critical role in mass, but neither of them has been seen. The first is the graviton. The graviton is massless, so it zips along at the speed of light. It cannot be actually spin zero because light bends around the sun, and that just doesn't work with a spin zero particle interacting with a spin one. So the simplest case would mean that it's got to be like spin 2. Now it could be spin 4 or 8 or 6, okay, but we're going to say nature seems to like simple things, so probably spin 2. The standard model, as originally conceived, has only the massless particles, and that is in violent disagreement with observation. All kinds of particles have mass. So the symmetries had to be preserved in that standard model while bringing in the mass. So a gang of 6 different physicists had the same idea, a spin zero field, and that was later got to be known as the Higgs boson. Nature may actually have a more complicated collection of particles up her sleeve, but so far none of those cards has been seen whatsoever. And I may have to make a big comment to this post if that changes anytime soon with the work being done at the Large Hadron Collider. So the first job of the Higgs is to provide mass to particles involved with a weak force. That would be the W plus, the W minus, and the Z. And perhaps using this Yukawa potential, the Higgs could provide a mass to a long list of fermions. Of course, if no Higgs has been found, then all bets are off. A Lagrangian is a way that energy can be traded inside of a box. And here is a list of things that I'm looking for in a Lagrangian that deals with mass. First, where is the home of the gravitational mass? And second, where is the home of the inertial mass? And then the third thing to look for is, geez, why does the equivalence principle have to be there? Why is it necessary? And fourth great thing would be to have some sense of what the heck mass is after all. So 2 Lagrangians are going to be looked at with that list in mind, general relativity and my own work with GEM. Einstein guessed at his field equations. All right, Hilbert did it the right way. All right, he derived the field equations from the Lagrangian, and here is in fact the entire thing that they spent all that time talking about. All right, it's just like 2 letters long. There's the Ricci scalar there, and this matter Lagrangian. That's the L with some M. Now I could say that was elegant, but that would only be a half truth. The Ricci scalar R right there is elegant, okay? Now one could spend an entire academic career They're studying the Riemann curvature tensor, whose contraction of a contraction is the Ricci scalar. What happens after a vector loops around curved spacetime and comes back to home? Well, it's the Riemann curvature tensor that tells you what that story is. The other term in there for matter fields, that's not so elegant. There is far more freedom to do whatever you please, either simple, like a cloud of non-interacting dust, or more complex, which is basically anything else. The Riemann curvature tensor is complex due to the intricate rules of the math machinery. The paucity of guidelines for the matter Lagrangian is a greater challenge. I mean, the mystery black box of general relativity is the matter term. So let's pick apart this two-letter Lagrangian. The gravitational mass that goes into the Ricci scalar, and that's it. It's gravitational mass, it's Ricci scalar. In a vacuum, the curvature of spacetime all flows from that Ricci scalar. Oh, that's very simple. The inertial mass is somewhere in that matter Lagrangian. So it's straightforward to justify the strong equivalence principle in the vacuum, since the only player on the stage is the Ricci scalar. It's like, oh, that's pure geometry. But with the matter contribution, the story might get more complicated. I mean, to be honest, I don't have a deep enough training in general relativity to know if they build in some safeguards into that matter Lagrangian to assure consistency with the strong equivalence principle. I mean, I bet only matter Lagrangians that get published are consistent. But, what about pathological Lagrangians? I mean, how do you deal with them? Know how to deal with your less than stable folks is important in figuring things out. So let me show you the Lagrangian for my own work. All right, there we go. So that's got these two scalar terms, hypercomplex guy minus a quaternion guy in the currents. And then it's got these field strength tensor dudes that look very similar, del A, del. It's just the multiplication is different, and there's actually an additional factor of conjugate in there, which is kind of interesting that we don't use always the same conjugate, okay? All right, so the gravitational mass is in the terms with the hypercomplex products, those box times sort of things. And that thing actually depends, the field strength tensor things, the del A thing, has this as a gauge, all right? And it's pretty simple gauge. It's d phi dt minus del dot A. That's what it, that appears in that term. Now, the inertial mass hangs out with the quaternion products. That would be the guys that just had the cross in there. And the quaternion field strength has exactly the same gauge dependence. And the exact cancellation, because there was always a minus sign in there, of the gauge terms between the hypercomplex and the quaternion field strengths means that the most pathological choice of a potential or a really whacked out Byzantine manifold to take your derivatives will not break the equivalence principle in both senses of the word, both the weak and the strong sense of the equivalence principle. So, can we finally stand on a solid rock, reason why there is mass? Sorry, but I've kind of been trained to underplay my cards. The most important message for the general audience is that this gem work provides an utterly different reason for mass than what is on the market today. The Higgs mechanism is a solution that plays nicely with all the work on the standard model. Now, the gem work plays great with Maxwell. I mean, they are, in fact, good. It's a good symmetric twin of Maxwell. But it really flips the bird to GR, and it keeps the symmetries, but really drops the tensor products that are found in the standard model. So that's basically not playing well with anybody who has a job in either of those fields. So the ice out here is really quite thin as far as getting to why there is mass, but I'm going to give it a try. So particles in the universe, most of them just don't have mass. And by most, I mean, if you were to take 10 billion particles chosen at random, only one of them has mass. I mean, we really are in a minority. But the universe isn't structured like randomly, like at all, okay? Stuff with mass hangs out with stuff with mass in planets, in stars, in galaxies. The massless do not really have a story to tell. For them, a change in time is the same as a change in space. Now, contrast that with particles with mass. They can tell you a story. They can drone on and on and on. For a relativistic velocity between two particles that are near unity, the story's got to be really brief. Whoa! Okay, but if a particle actually has a relative velocity to you that's almost nothing, well, then you can go on and on. They have to listen to you, unless they have enough energy to leave. But if you think about the stuff that we've shared time on the Earth with, all these atoms in the atmosphere right here, we've hung around together for like at least 4 billion years, and we might have been in the same star that went supernova, and it gets kind of crazy. So this is a piece of art that's in my dining room, actually, the speed of light, according to Rene Magritte, and it really says that kind of message. I mean, I get this message every day with my gluten-free waffle and maple syrup. There's no time without space, no space without time. Let's see, the top line is the speed of light, c is not a velocity, but the key thing for this discussion is side panels where time eclipses space. So if you got a really long amount of time, you can tell a really long story. And if time is space, you get one chance to exchange one bit of information, and then that's it. Okay? So does that really answer the question? The answer is no. Okay? This is just really this is just the edge of what I know about this subject. So let me bring up my snarky puzzle. So I want you to work with a pathological potential. The potential would be A equals t squared minus 2x minus 0.4 y to the cube minus 0.2 z squared. So I want you to calculate the differential with a quaternion product on this potential, and then I want you to do that but subtract the conjugate of that. Then I want you to flip the order of these things, and then flip the order of these things and subtract the conjugate of that, and then I want you to take the symmetric product of that, first taking the conjugate of the differential, and then I want you to subtract away, and you're going, hold it, time. Isn't that a lot of stuff? No, go to the blog and see the full list. Okay, it's 8 in all, and it's really not that bad. Why not? Well, it's not that bad because what you can do is, once you figured out one, then all of the other ones involve either something going to 0 or flipping a sign of one of those terms, and that's kind of it. All right. Now, to do the next step, you'd have to download my software and install it on your computer, and that's way too much work, but I'm going to do it because it's on my computers. But you take the group U1, which is just a unit circle in a complex plane, in the direction of 1, 2, 3, 4, and feed that into this group of quaternion polynomials, and make animations, 8 animations in all. So, you know, there should be one obvious property for the ones where the gauge goes to 0 because you're doing that subtraction thing. They'll have a very specific quality to it that I call blink, okay? And that's kind of interesting that the blink guys all are the ones that I think might be involved with being massless. So, all right. So anyway, that's the story from here. So thank you very much.